Welcome. Every linear programming problem has a corresponding dual problem. This dual problem is again a linear programming problem. One important fact about the dual linear programming problem is that if the original linear programming problem has a solution, then the optimal value of Z obtained from the original linear programming problem will be the same as the optimal value of Z obtained from the dual problem. There are also other common features we can observe from both of these linear programming problems. Sometimes solving the original problem is easier, whereas sometimes solving the dual problem is easier. Therefore, it provides us convenience in obtaining solutions to the linear programming problem. In these notes, we shall only consider maximization problems with constraints with less than or equals to symbols. Suppose we are given a linear programming problem, which is a maximization problem with constraints having less than or equals to symbol only. We call this linear programming problem as the original problem. We are going to present the method to obtain its dual problem. Please refer to the following guideline by yourself. This gives us the rule on how to form the dual problem. It can be best explained by using a concrete example. So we shall first refer to a concrete example and we shall revisit this guideline again afterwards. Suppose we are given the original linear programming problem, which is a maximization problem involving all the constraints containing less than or equals to symbol. This original linear programming problem is to maximize Z equals to 3x1 plus x2 plus 4x3 subject to these constraints where x1, x2, x3 are non-negative. We can use the following method to obtain the dual problem from the original linear programming problem. First, we construct a matrix with entries that can be obtained from the original problem. We first refer to the constraint inequalities from the original problem. We use the coefficients and the right-hand side value of each of these three constraints to fill up the first three rows of the matrix. For example, since the first constraint is 3x1 plus 5x2 plus 10x3 less than or equals to 120, so the first row of the matrix will be 3, 5, 10, and 120. The second constraint and the third constraints are written similarly. Since there are three constraints, therefore, so far we have filled up three rows. Since we have three variables, therefore, together with the right-hand side values, there are altogether 4 columns. After that, we refer to the objective function of the original problem and use the coefficients of the variables to fill up the last row of the matrix. In this case, the objective function is Z equals to 3x1 plus x2 plus 4x3. Then we refer to 3x1 plus x2 plus 4x3 and fill up the last row with the coefficients 3, 1, 4. The last entry of this row will be empty. We simply write a 0 to fill up the space here. These positions are written in the position which refers to the corresponding column represented by the variables involved. Please be careful that when we write the objective function to the last row of the matrix, we directly write the coefficients of these variables to the last matrix. We do not include Z, so there is no need to write coefficient 1 for Z here. Also, we don't need to move this expression to the left-hand side of the objective function, we directly write 314 instead of -3, -1, -4. This is different from the way that we write the objective function in the tabular form in the simplex method. Also, please write the expression from the objective function to the last row, but not to the first row. The matrix is now completed. Let us denote this matrix by M. Since this system has 3 variables, the matrix M will have 4 columns because we need 3 columns for the variables and 1 column for the right-hand side value. Since we have 3 constraint inequalities here and 1 objective function, therefore the matrix M contains 4 rows. Step 2. We obtain the transpose of M. In our example, the transpose of M will be this matrix. The ith row of the matrix M becomes the ith column of the transpose of M. Step 3. We can obtain the dual problem by reading the information from the transpose of M. In our case, the transpose of M is a 4x4 matrix. The first 3 rows will give us the information on the 3 new constraints in the dual problem. Since there are 4 columns, the first 3 columns give us the information on the coefficients of the 3 new variables, and the last column gives us the information on the right-hand side value. The last row of the transpose of M will give us the information on the new objective function of the dual problem. For the first row, we have 3, 5, x, 3. So in this dual problem, the first constraint will be 3y1 plus 5y2 plus xy3 greater than or equals to 3. The important point to remember is that in our example, the original problem is having less than or equals to constraints. Now, in our dual problem, the constraints will have greater than or equals to symbol instead. For the second row and the third row, it corresponds to the second constraint inequality and the third constraint inequality of the dual problem. Now, we refer to the last row of the transpose of M. We ignore the last entry 0 because it is just for filling up the space of this matrix. We have 126 and 105. This becomes the coefficients of the variables in the objective functions of the dual problem. So we will get 120y1 plus 6y2 plus 105y3, which is the expression for Z. One important point is that our original problem is a maximization problem. Then our dual problem will be a minimization problem. Therefore, our objective function in the dual problem will be to minimize Z equals to this expression. Please also notice that instead of naming the variable as x1, x2, and so on, we have new names for the variables of the dual problem. Here we use y1, y2, and so on. The reason is that they are different from those variables in the original linear programming problem. Therefore, after performing step 3, we obtained the corresponding dual problem as follows. And this dual problem is again a linear programming problem, and it is a minimization problem with constraints having greater than or equals to symbol. Let's refer back to the guideline on page 3 of the lecture notes. We can see that originally we have a maximization problem with all the constraint inequalities having less than or equals to symbols. then the corresponding dual problem will be a minimization problem with all the constraint inequalities to have greater than or equal to symbols. But please notice that for both the original linear programming problem and the dual problem, we still assume that all the variables are non-negative. Point 2. For every variable in the original problem, we get a constraint in the dual problem. In our situation, in the original problem, the terms involving the first variables are 3x1, 5x1, xx1, and 3x1 from the objective function. This gives us the information to build the first constraint of the dual problem. So the first constraint in the dual problem becomes 3y1 plus 5y2 plus xy3 greater than or equal to 3, where this comes from the coefficients of x1 in the objective function of the original problem. Similarly, in the original problem, the terms involving the second variables give us the information to build the second constraints of the dual problem. The third variables in the original problem also give us information to build the third constraints in the dual problem. Next, for point 3, for every constraint in the original problem, we get a variable in the dual problem. In our situation, the first constraint is 3x1 plus 5x2 plus 10x3 less than or equal to 120. This gives us information to construct the terms involving the first variable in the dual problem. So, the first variables in the dual problem will have 3y1, 5y1, 10y1, and 120y1, which comes from the right-hand side value 120, and it becomes the term involving y1 in the objective function of the dual problem. And you can double-check that the second constraint in the original problem gives us information on the terms involving y2 in the dual problem, and the third constraint in the original problem gives us information on the terms involving y3 in the dual problem. Point 4. The coefficients of the objective function in the original problem, which is 314 in our case, becomes the right-hand side constant in the constraints of the dual problem. So we have 314 here. Point 5. The right-hand side coefficients in the constraint in the original problem, which is 126 and 105, becomes the coefficients of the objective function in the dual problem, 120y1 plus 6y2 plus 105y3. The last point, the variable coefficient in the constraints in the original problem becomes the variable coefficients in the constraints of the dual problem, but the rows becomes columns and the columns becomes row. You can double check these conditions by yourself. Let us jump to page 6 and consider the example and illustrate with our method of generating the dual problem once again. So we are given the original problem, which is a maximization problem. The objective function is z equals to 5x1 plus 6x2 minus 2x3. And there are constraints involving less than or equal to symbol, and all of these variables are non-negative. So first, we fill up the matrix with the two constraint inequalities, and in the last row, we've used the coefficients of the objective function to fill up the last row and fill the last entry with 0 to fill up this space. Next, we construct the transpose of this matrix M. This time, the transpose of the matrix becomes a 4x3 matrix. It means that there will be 3 rows that refers to the new constraints of the dual problem, and 1 row which corresponds to the objective function of the dual problem. And since there are 3 columns, it means that in this dual problem, there will be only 2 variables, and the third column represents the corresponding right-hand side constants of those constraints. Therefore, if we read those information from the transpose of this matrix M, we read the corresponding dual problem. The following give us the general information on how to construct the dual problem using the information from the original problem. And this is the general format of the original problem and the corresponding dual problem. You can verify how to construct the general format of the dual problem by using the 3 steps we have mentioned before involving the matrix and the transpose of a matrix. Please verify it by yourself. Please try the following exercise to construct the corresponding dual problem for each of these linear programming problems by yourself, and check the answers in the following page. The following are the solutions to the exercise in the previous page.